This assessment asks us to show the mechanism of a retroclason reaction used in the biosynthesis of myristoyl-CoA. Now, anytime we look at a new mechanism, and first of all, calling it the retroclason tells us it's essentially going to be the clason reaction in reverse, but we can use the color coding on the screen to see what's happening in the reaction. And you'll notice that this shaded carbonyl here, originally attached to all of this that's in pink, is going to be replaced by what is here, this HS-CoA. Now, if we look at this, think about the innate reactivity of this carbonyl, we know that that carbonyl is going to be electrophilic. So we need to start our reaction by somehow turning this into a nucleophile. Now, the problem, the assessment tells us that we can use an active site base, so we can just use B- to say that some base in the active site of the enzyme can be used in this reaction. And so we'll start by deprotonating it to make this S-CoA a good nucleophile. And again, the identity of the CoA, right, that's a big, complicated organic molecule. We'll just keep it abbreviated as such. Well, from here, we now have made a better nucleophile that could conceivably attack this carbonyl. I'm going to redraw that so we can have a little more space to show the mechanism. This is our 12CH2, so this carbonyl here represents that one. We can now have this attack. Now, why do we think this is going to attack? We think this is going to attack because the mechanism, the reaction on screen is telling us this, right? It's telling us that sulfur gets attached to that carbonyl. Now, when this attacks, we can form a tetrahedral intermediate, or at least we're going to think it's a tetrahedral intermediate because it's not going to stick around. But that gets us to here. So we're almost finished the mechanism. The only thing we need to do now is to lose this part of the molecule and reform our carbon-oxygen double bond. And maybe this doesn't look like a reaction that we would expect to be favored, but in the active site of the enzyme and using Le Chatelier's principle to drive some of these enzyme catalyzed processes, we know that this must be what's happening. And so the lone pair on oxygen is going to collapse down and kick out this group, this enolate, as a leaving group. That's going to complete formation of the myristoyl-CoA and produce this enolate. This enolate, right, we have to now protonate it. We have that active site. It was originally the active site base. Now it's the conjugate acid of that active site base. That's going to be what is used to protonate to give us this ester. This is the mechanism of the retroclason, and we see that it's a retroclason because we're essentially having the ester as the leaving group when normally the ester is the nucleophile in the clason.